to a very brief day. Nice to see so many people here. So the first talk will be by Antonin Chambolle on remarks on the discretizations of the perimeter and total variation.
Thank you. So I thank the organizers for giving me this opportunity to talk here and return to Cambridge, which I like very much. And what I will talk about is things which came out when studying a bit really in detail the discretization of the perimeters and total variation, first with Thomas Pock, because we wanted to discretize more complex like curvature dependence or whatever similar functionals, and it was always, the results were always very bad and are still bad, so we did not understand much yet. And then with Corentin Caillaud, where we did with a student in CMAP, and we did some error estimates for common discretizations of the total variation. So it's a topic I've been interested for many years, and maybe I'm sorry because maybe it's not so interesting. It's really my interest. So the issue is to understand better some simple numerical approximations of the total variation and the perimeter functional. So as I said, the goal is to extend to more complicated functionals, but it's still far. And the issues I'm dealing with are two main issues. So one on which we don't have so much progress, and one which we understand better now. So one is the anisotropy of even so-called isotropic discretizations. And the other is the quality, and maybe I'll have a few slides explaining this. It's the quality in terms of if you want to do solve Dirichlet problems, so we want to extend and find, for instance, minimal surfaces or lines in 2D. And usually with most of the discretization you get very blurry results, and it's something we don't really control yet. So so I will discuss finite element and finite differences discretizations, which maybe is bad because maybe you get better results if you discretize on graphs, but it's always very anisotropic then. So, and the first point I will talk about is to understand how to better discretize the gradients, and this naturally gives you representation in terms of non-conforming P1 elements, so it's something I will describe. And this has quite good properties, but also some drawbacks. But then it led us to understand that you can get very different error estimates depending on representation which look quite similar at first hand, or quite both natural, I mean. So what is difficult when you want to approximate the total variation? What is difficult is the fact that you expect when you minimize the total variation plus any other term, Dirichlet data, whatever, to get sharp transition, so boundaries. It's also a way, for instance, to regularize boundaries in shape optimization problems. So you need to approximate sharp transition if you want to get nice results. At least, for instance, in imaging, people want to get not blurry but sharp results usually. And also, which is more or less the same issue, when you have a set with a discontinuity. Of course, if you look at the small scale, you don't expect to be able to approximate accurately the transition, and that's essentially why it gets blurry in general, because if it's blurry, it's easier to accurately represent the perimeter. So let me give an example. So almost everybody is using this, for instance, in imaging, to approximate the total variation. So you just take your favorite discretization of the gradient, for instance, forward differences, and you take the L2 norm, the Euclidean norm, and you can do that in any dimension. And actually, it's a good idea in some sense. So we could prove, and I'll show it in the end, that in fact it's not such a good idea, but it's a good idea because it is isotropic. It doesn't look isotropic, but if you take the limit when your grid goes to 0, it is an approximation of the total variation. So maybe the simplest is to understand this as gamma convergence. So you send your pixel size or your grid size to 0, and when your function converges to some function, then this gamma converges to the total variation. So if you minimize a problem with that, you're minimizing essentially the total variation. which is what you expect. But of course, the limit is not pointwise, and this has been observed at least since 20 or more years. And it's not isotropic at fine scale, which is a bit the same. So the example is obvious. You consider just a diagonal line, and you measure, and you assume you really have a sharp transition between 0 and 1, and you measure the energy. So on the left, here, since you're taking these differences and then taking the square root, here you're measuring square root of 2, which is precisely the length you want to measure, so it's okay. And here you get a global length. If this is of size 1, you get a global length, which is square root of 2. But on the right, since you're taking these differences, each time there is only one edge which is crossed in your differences, so you're measuring 1 for each of these. And in fact, in the end, you're measuring a length 2, which of course is wrong. So, of course, if you minimize something, you will never see the right hand appear, because you can do better. And what happens if you want, for instance, if you do a proof of gamma convergence, the simplest way is to do the proofs on smooth function, which is a pointwise limit, and then you do some smoothing. If you don't have a smooth function, you approximate with smooth function. So what you do is smoothing, and numerically it's exactly what happens. If you have a solution of any problem with solution, for instance, is this disk, then you will see that in the good directions, which are these directions, then you actually get something very sharp. But in the bad directions, if it were sharp, you were overestimating a lot the measure of your disk, so you don't do it. And you smooth your disk, so you get this result, which is not so bad actually, but visually it's not very nice. And in terms of energy error, the error is, it's good. I mean, this is approximating correctly the length, the perimeter. But in terms of precision of the result and even of error, we will show, in fact, we can show that here the error is large in some sense. Okay, so there have been many proposals to improve this finite difference, this kind of drawback. So, for instance, it's something I did with Stacy Levine and Brad Lucier a long time ago. I mean, it was an idea of Lucier to try to do some upwind finite differences, which is not very natural in this context because it's mostly elliptic problems, and you get results which are not symmetric if you replace u with minus u. But visually it's good, but we did not really have error bonds, neither here. I mean, you could have standard error bonds, which I will discuss later. There is an interesting, I will not discuss that, but there is an interesting proposal of Abergel and Moisan, which is to upsample the image by doing some interpolation in Fourier and then try to estimate, and they can estimate the total variation of that, and then work with this strange functional, and it's very good for getting results without any ringing effect. So they get very nice results on small structures. And there is a strange paper of Laurent Condat, which in fact now we start to understand, and we can understand in terms of some dual representation, in terms of, but it gives. It's only there are no proofs. It's just a proposal and then a study and an optimization scheme. But it's very, very isotropic. So I will discuss it a little bit, not probably very precisely, but in the sense.
Anisotropic, I see. But very isotropic.
No, this is a bit isotropic. I mean, you get. What I mean is that here he did a lot of experiments. So the experiments which are difficult are this kind of experiment. You take, for instance, you take a boundary datum, which is just half plane, and you try to minimize the total variation. So you should get this line. And he did that with many different orientations, and he gets always very nice results. And that's quite amazing in this context. But it's mostly an experimental study. And what Corentin Caillaud is looking at is a simple variant which is less good practically, but for which you can show error bonds which are quite good. So I hope I can explain a bit this in the end. Okay, so There are also quite a few papers where people approach this with finite elements. Most of the time, one first point is that you wouldn't use very high order finite elements here, because when you minimize the total variation plus anything else, you never expect to have a function which is better than Lipschitz, and very often discontinuous. So it's hard to use high order because you would need to use them in the right place and do things like that. So no one is really doing this. Maybe there is a way. So usually you use P1 elements, maybe some P0, so it means piecewise affine, piecewise constant, or whatever. So most of the works on finite elements essentially use a primal P1 conforming element approach. So P1 conforming means really you have a continuous piecewise affine function and you just measure the L1 norm of the gradient and you use this as a functional. There are some variants, maybe I should not discuss this now. There are a few, but not so many. So there are some proposals, so even an old one of Repin, of using discontinuous P1, but measuring really the total variation including of the jumps. And in fact, it's almost the same as P1. It's really conforming, and it has the same drawback I will mention. And there are a few dual approaches which work, but I think they are too complicated in some sense with respect to what really should work. So with P1 elements, what is the issue? It's about the same as with the finite differences approach I mentioned first. If you have a set, and you have so for instance you have 1 here, 0, and you have triangles. If you just approximate this plainly, so you will put 1 here, 0 here, you see that the gradient is essentially an arrow in this direction, and what you're measuring is precisely the length of the middle segment here. So if you do that for all your mesh, maybe, then you're measuring a kind of line which is jagged, and it's completely mesh dependent. And what you get is that the total variation you build here is essentially the length of this polygon. So it's always larger, at the first order it's always larger than what you would expect. So you need, again, to smooth. And so as I said, the total variation is like the perimeter of this polygon, which is based on the triangulation. And if you do that in practice, same experiment, you see that in order to get a good result, you have to smooth, so you have a transition which is not so sharp. And you also see that essentially the level lines are quite jagged. Okay, so P1 is not great in that sense. And if you use discontinuous P1 and measure the jump, it's the same, essentially the same, because you're also introducing jumps, but they are constrained by the grid. This is the first idea we had, and now we understood more things, so maybe we'll forget about it, but I still explain it. What is the basic idea you could do? So a better idea, if you want to improve the discretization of the gradient, should be to discretize directly the gradient and not the function itself. So what we thought about is what happens if we just take the average of the gradient on each triangle. So we do a P0 approximation of the gradient, and we measure that, and we measure this as the total variation. Then, of course, by using Jensen inequality, you get something which is lower than the total variation of your function if you project it this way. So this G is simply what would be called the P0 function, so it's the average of the gradient on each triangle. This can be, I'm talking about triangle, you can do the same in any dimension, it doesn't change much. And if you consider the orientation of this piecewise constant vector field and the original orientation of your gradient, then in fact you even have an equality which looks like this. So you have that this measure is exactly the total variation plus something which depends on how much you oscillate in each triangle. So if you don't oscillate, for instance, it's perfect if you oscillate. So it gives you quite good error for the energy. For instance, if you have a set like that, and you take the average of the gradient, so essentially it will be 0 everywhere except on the boundary, and you measure this, then you see that you get something which is below the perimeter, but it's also larger than the perimeter plus some term which depends on the curvature. So if you have interior and exterior ball condition of certain radius, so total curvature bounded by 1 over r, you get an error which is like h over r square. So it's not so bad. And the point is that here I have discretized the gradient and I want to link that to some function because the gradient field is not something very practical. And in fact it's very simple and it's well known. What we are doing is simply doing an approximation which is called non-conforming P1 finite element or Kruse-Raviart. So it was introduced by Kruse and Raviart around 70 or something like that. And what they introduce is a set of finite elements which are continuous only at the middle points of the facets of your triangulation or mesh or tetrahedra or whatever. And projecting a function onto this is simply taking the average on each facet and putting the value in the middle. And if you do that, you're exactly taking the average of the gradients. It's very easy to compute, to see. And it has been observed a few times, for instance, in nonlinear elasticity, that it was nice to discretize nonlinear energies of a gradient, because if you have any convex nonlinear energy, you get more or less what I said, that you get something below and that it's very close if you have the oscillation. I mean. So, and also you can characterize Kruse-Raviart gradients in a simple way. So in 2D first, in 2D it's very easy to see that it's orthogonal to rotated gradients of P1. It's a very simple computation. But in any dimension you can see that it's characterized by duality with zero divergence vector field, except that you should take what is called zero order, first order Raviart-Thomas vector fields. So it's, I will explain in the next slide what this is. So if you have a field is a gradient of a Kruse-Raviart function if and only if it is orthogonal to all these lower order. And it's something which I guess is known, but we haven't found it. We have found, the closest we have found is a recent lemma of Carstensen and Liu, 2015, in 2D. But the proof is very simple. And what is a Raviart-Thomas for people who are not too familiar with finite elements? The idea is to try to discretize a vector field with a conforming divergence, means you want the true divergence to be defined, to exist. And the way to do that is to use that as degrees of freedom of values, the flux on each edge, and to take fields. For instance, this flux will be generated by a field which is parallel here to the edges, so that it has no divergence when I jump here. Sorry. So this field, what happened? I was pressing this. So the field generated by this edge here, by this flux, is a field which is parallel to the edges here and zero here, so it has no divergence here. It's discontinuous, but it has no divergence. And then it points like that, but the normal component is always constant here, so the flux is essentially a constant on this edge. And then you just take the opposite here, you get back here. So it's defined like that. So it's really a very simple notion of piecewise affine fields which have a true divergence. So and it's the one you use in this duality. So okay. So we introduced this Kruse-Raviart total variation as the total variation of the gradient of the Kruse-Raviart function, without taking into account, of course, the jumps on the edges. This would be a more conforming P1 if we were taking into account the jumps. So it's not the true total variation; it's below the true total variation of the We also introduced, and I will explain why it was convenient to introduce for a P0 function, so a piecewise constant function. We introduced the minimal total variation among all Krauser-Ravier functions which have this average. So you consider a constant function here, and you look at all the affine functions which are continuous through here, but have essentially this value in the middle, a fixed value in the middle, the same as the average. And you take the minimal, the minimum of this. And you can show that with these two definitions, you still have a kind of gamma convergence property. So this approximates the true total variation as the mesh goes to 0. For compactness, it's more complicated. If you have arbitrary meshes, you will get compactness only in the distributional sense, so it's very weak. You could have wild oscillations. If you have meshes which go to 0 with some angles which are bounded from below, then you get a control, you get a stronger control, and you get L1 compactness. You still have this kind of error. Okay, maybe I can skip this. So there are two properties which are interesting of this total variation. So that's why first we thought it was very nice. One is that you have a duality formula which is very simple. So I introduced this P0 variant, which by definition it's always less than the Krauser-Ravier. So this is the minimum over all Krauser-Ravier which has the same average on the triangles. And it turned out that this P0 variant is exactly defined by duality with Ravier-Thomas fields. And this is interesting for computing error bounds and also numerically. Means you can do very simple reconstruction with this T0 energy. And the other property which is quite nice is about this kind of problem. But then maybe I'll explain that it's a property which is shared by more discretization than just this one. But it was first a surprise when you saw that. If you take any direction here and you solve this problem with any mesh here, and with this discretization, this Krauser-Ravier discretization of the variation, then you always get the exact number. You always get the length. We found that very strange, but in fact it's obvious because it's essentially because here, if you have a straight line, then the normal vector does not oscillate. So essentially your representation is exact here. Even if in practice we were disappointed because for this kind of problem, if you just take an arbitrary mesh and do a Krauser-Ravier, there can be in fact, and we can show it on some examples, there can be many solutions. There can be non-uniqueness, and even if there is always a solution which is sharp, which corresponds to the exact projection of your sharp interface, so you do the Krauser-Ravier projection of the function 0, 1, there are also usually functions which have a transition, which of course goes to 0 as h goes to 0, but which can be quite large. Maybe if I have time, I can illustrate this with an example later. So an example, and you see also one of the drawbacks of this approach. If I take the same problem as before, but I solve it with this Krauser-Ravier discretization, I get a much nicer edge if you look at the orientations. This is a very smooth change of orientation here. I get also a slightly smaller transition. So, for instance, here you see that the transition is like over 6 elements maybe, and here it's over 2 elements. So you get also a much sharper transition zone. But you lose completely the values here. That's the problem with this approximation. It's a kind of Heisenberg principle. You're more precise in terms of gradient and orientation, but then it means you don't have the values. And I'm not sure you can do better. The only thing you can do which improves this a bit is to consider the average, this P0 approximation, because then the average looks somewhat a bit better. But then again, you will lose the orientation if you do that. Or you have to keep both. should keep the gradient and the average probably as a representation. Okay, so now let me talk about error bounds. To compute error bounds, we first have focused on this problem, which maybe is not the best in this context, because, for instance, if we just want to solve a Dirichlet problem, we see that we have an almost zero error bound in terms of energy, or zero error bound in terms of energy. But since there is non-uniqueness, it's not so easy to understand what would be an error bound in terms of the function. So this is probably quite hard to study. So we consider this kind of problem, which in the imaging literature is called Rudino-Scherfatemi problem, which is simply minimizing the total variation plus a quadratic term. And the advantage of that is that you have a unique solution, whatever you do, because you have a strongly convex here problem. So it's reasonable to study error bounds also for the function here. And we can solve the following. So the first result is a very classical result. It's simply saying that, so if you have the true solution and H discretized solution, so H is the size of your triangles, and I use for solving the discrete problem, I use this TV0, so I use a P0 representation, because here it's much simpler. So the first result is saying that if you have a BVG here, you get essentially in L2 norm you get H over 1/4. So in terms of energy you get square root of H as an approximation here of your. So why this is classical, this dates back to result, for instance, of Lai, Lucien 1. It's a very classical proof in the sense that here what you do simply is smoothing your function, computing an error bound for smooth function, and then optimizing the smoothness to get your thing. So this is a classical proof. And here we have to assume that G is BV. If you assume, you have to assume some continuity property of G, that G, the distance between G and its, for instance, P0 projection should be controlled if you want to do that. But there is another kind of thing which is more interesting, I think, in this context. Of course, it's based on an assumption which is a bit problematic, but I will explain that afterwards. But if your dual problem, so I will give it in the next slide, as a Lipschitz solution, then you can get H over 1/2. So you can get H, which is probably optimal here because you're projecting in P0. So you can get H error for this energy and H 1/2. And the only other paper where you have H 1/2 is a paper by Bartels, Noceto, and Salgado, where they have a similar problem and they prove H 1/2, but they are cheating a bit, I must say, because they are using an L1 total variation, meaning the integral of the D1U plus D2U, and you do that on a square grid, and in that case, it's easy to show that you can approximate it very precisely, exactly, essentially, for piecewise constant. Okay, so what do I mean by the dual field as a Lipschitz solution? So there is one issue in this result, because I don't know any general result showing that given conditions, so that there is a Lipschitz solution to the dual problem. And I tried a bit, but I think it's hard. So the duality, how is the duality for this problem? So in fact, you have to use the dual definition of the total variation, which is a soup of Z so it already was, I think, in Samuel talks. So you take the soup of integral of U divergence phi, or which is, I can put a minus here, which is like phi du if you want. For phi, you would say for phi norm less than 1. So and if you use this duality, then you can see easily that this problem has a dual which writes like that. So it's the max over fields of norm less than 1 of the L2 norm minus the L2 norm squared of the divergence plus a term involving the source term, the G. And here Z should be less than 1, and at the optimality you have that Z that is here phi du is the norm, so z du is the norm of du on the support. So here du are measures. Du is a measure, but this can be given a meaning. And of course, z here is in general non-unique. Why? Because so first, if g, so I assume always that g is L infinity. When g is L infinity, it's easy to show that there are always flat zones in the solution. So U has areas of non-empty interior where it's constant, which correspond exactly to areas where Z can be anything of norm less than, oh, there is a mistake, which is a very strange mistake. Of course, what is not, this is less than 1. Z must be less than 1. No, I don't know why. This is awful because it's essential here. And in fact, when you have a flat zone, it's precisely where Z will be less than 1. Essentially because you have a flat zone, for instance, a maximal zone here, and the gradient here points in this direction at the boundary, and Z should be pointing like this, and here it must go from here to here, and usually it goes from here to here by going to 0. And where it's strictly less than 1, then obviously it's non-unique because you can have any small perturbation with 0 divergence and you get another admissible Z. So it's unique on the level lines essentially, but it's non-unique everywhere else. And but on the other hand, the divergence is bounded, if G is bounded, because the divergence is given by U minus G. And for instance, in 2D, it's clearly Lipschitz on the support of the measure du, because there the divergence is essentially like the gradient in 2D. But for instance, if you have in 2D like that, you would have that here you get bounded curvature and then a Z which has a bounded gradient, but here you don't know. And for instance, if this flat area could be very small, then you could expect that there are, the Lipschitz constant is very large. Or that is, but you don't expect that this happens, in fact. So in 2D, I'm not even sure. In 2D, it could be that when G is bounded, Z is always, there is always a Lipschitz Z. I don't know about that. In higher dimension, it's complicated. But what is interesting is that you can build a lot of explicit examples where Z is Lipschitz, or one Z, at least one solution is Lipschitz. The most simplest and which is well known since many years is the characteristic of a ball. So if G is the characteristic of a ball, and to simplify, I consider the whole space, then the solution is explicit in that case. You can take Z equal essentially X inside the ball and something decreasing with 0 divergence outside the ball. And you get an explicit solution which is given by this. Okay. And the Z you're building here is 1 over R Lipschitz, for instance, in that case. So there is a Lipschitz solution in that case. So if you have a Lipschitz dual field, then so I use here the P0 Crouzet-Ravière variant, so the average Crouzet-Ravière. You can show that the solution is bounded by CH. And this is not too difficult because on one hand you get a primal bound using the fact that your total variation, your discrete total variation is less than the continuous total variation. And for the other bound you use a dual problem and you discretize your dual vector field. And what you do is that you discretize it as a Ravière-Thomas field. And to do that, you simply have to take the fluxes on all the edges and say that this is your Ravière-Thomas vector field. And it's like taking the average of the divergence in each triangle. So if you take the fluxes here, and if you remember, probably you don't remember, but if you remember the duality formula is asking that your Ravière-Thomas field has norm less than 1 in the middle, or on average. So if you discretize, if you consider the fluxes here, if your field is not Lipschitz, then you could have, for instance, a field which is turning very fast here. And here it has a large flux, it is a rare flux, and here in the middle you would get a very large vector. It can be up to square root of 2. essentially, as the norm. So you don't have a vector with norm less than 1 if you don't have. But if you have a Lipschitz constant, then this cannot happen, obviously. And here you get a norm which is 1 plus ch, essentially. So plus Lipschitz constant times h. So it's very simple if you have this assumption. And you get this error. Okay. So now, there's something interesting, I think, which is, so what happens if you go back to the isotropic total variation I was mentioning in the beginning of this talk, because we thought, okay, maybe it's different for this case, but it was not completely obvious to understand why, because it means you have to compute lower error bounds, and it's harder than computing upper error bounds, so showing that you cannot do better than a certain rate. And in fact, for this isotropic total variation, we could design some experiment which allows to compute a lower error bound. So it's very simple, this drawing. So we consider an infinite domain, but we consider a periodic domain, which is a strip, a diagonal strip. And we consider a function g, which is 0 and 1 here. So it's essentially, when you remember this disk, we are essentially trying to look at what's happening here. So to simplify, we consider a flat thing here with 1 and 0. Okay. And we discretize that, and we consider the finite differences discretization with a gradient defined by these two differences. And to simplify also the calculation, it's exactly the same, but the calculations are much more complicated. We put Dirichlet conditions, so we put 0 here and 1 here. Normally, if you want to, for instance, to infer some result for the disk, you should put Neumann, because this is not really, but okay. So, okay. So here, if you consider this problem, so it's obvious that the minimizer will be translational invariant and increasing. So you get that, in fact, it's a 1D problem defined only by these values. It's a 1D problem defined by these values, and you use the fact that discretization is involving 3 consecutive values, and okay, so it's the next slide. So you end up with this problem, where you have here a norm involving 3 consecutive values. Okay, and the result we can show is that in this setting, the discrete energy minus the continuous energy, which is 1 here, you're jumping from 0 to 1, and you're paying essentially that, is larger than h to the 2/3. So this is the result you see here numerically when you see blurry result is really bad, because it's really, in fact, in terms of error, a large error with respect to the discretization. On the other hand, if you flip the experiment, so if you consider this strip now, then it's perfect. So here we have sharp result, because in fact we have a perfect approximation of our problem. So how do we prove this? I don't know if it's so interesting, but I will give some hint, maybe. So we want to bound this from below. So we have this minimum. We know that the optimum, the continuous optimum, is 1, because you're essentially taking u equals g, so the term u minus g is 0, and u is jumping from 0 to 1. Okay. So we want to show that this value is larger than 1 plus c h to the 2/3. So if we want to bound a minimum problem from below, it's not very easy, but as it's a convex problem, it is easy, because you can look at the dual, and it's enough to find some candidate for the dual. So we dualize the problem. So we introduce a dual variable for this quantity, a dual variable for this quantity. We do some operation. We find that the value is exactly the same as the value of this problem. So this is essentially my constraint z less than 1 in the continuous, in the standard dual problem, if you want. And by symmetry, we can remove one of these variables, because we have these differences are symmetric. And the point is that we did a lot of numerical experiments, and we say, okay, it seems to be of that order, but why? And we tried to look at this, and this is a bit complicated. But then we realized that if we separate this into a sum of and difference of the values of L, so it means an average and a difference of the values of S here, then this strange thing becomes a first order derivative plus a second order derivative. It's a simple calculation, but it's something we found a bit by chance. So you do this change of variable, and then with some scaling, but then the scaling, we tried many different scaling before understanding that this was the right one. And you end up with an energy which is essentially a continuous energy, if you rescale it by n2/3, of a very strange problem with some constraint. And why n2/3? Because if you take a smaller, I think it's smaller, if you take a smaller scaling here, you end up with a smaller scaling here, and you lose this constraint, because this constraint comes from the constraint t square plus s square less than 1. With this change of variable, it gives you something like this with n to some power which appears. And when you pass to the limit, depending on the scaling, you end up with 0 or with something. And when you end up with 0, then this minimum is 0, so you can't prove anything. So this is the first, 2/3 is the first value for which we have a constraint here. So then what we do, we study that, we dualize it again. So if you dualize, you get a strange problem also. But this strange problem is nice because it's easy to show that it has a positive solution and not 0. And that's what we wanted. So we study that because we don't just want to show that the value is positive. We also want to go back to the discrete problem. So to do that, we first show that we have smooth solutions to this problem. And from this smooth solution, we can compute a smooth dual solution to the previous problem. And once we have a smooth dual solution to the previous problem, it's very easy because we just discretize it and we plug it into the discrete problem and we get the value we want. So, and we really get that for some constant, this is large. So okay. I think that's all. That's what I say. So that's also something a bit strange because I think it's not the end. I mean, I won't spend years on this problem, but but I did some experiments, and the computer spent some time on the problem for me, and it seems it's rather -5/8 that I get, but I don't know why. So this could not be even optimal. So actually, when you do numerics, you really get a smooth transition, and it's really. So this is more or less what the limit problem will give you. You never have a sharp transition. Of course, the width goes to 0. And what about the case where you flip? So where you're here, but here it's much simpler because you have this thing, and you're looking again at these differences. But then by invariance, by translational invariance, the values here and here are the same. So the norm of this gradient is essentially an absolute value like that. So you get an energy where instead of the square root, you get something like this. And the optimal value is 1, and it's obvious. So let me show some examples. I shouldn't have started with this example, but okay. So this was an example to study the isotropy or the lack of isotropy when you consider this kind of problem for different orientations. So I fix a boundary value and I try to minimize this energy in the middle. And if I do standard finite differences, I get very blurry results, and then the next slide shows some figures, and the values are not so good. If I get a Kreuzer-Raviart, so here there is a because it's an adaptive Kreuzer-Raviart. I will explain this in the end of the talk. You get something quite sharp, but not that sharp. And as we will see, you get quite good values. And if you take this strange Conda approximation, then you get something very sharp, which is quite amazing. And you get also very good energetic value. So this is what you should get. This is what we compute. So for instance, for 45 degrees, it's perfect, but this is not too hard. There is a small error for 3 pi over. This is what forward differences would compute. And Conda is almost also perfect. It's a bit less good here, but same with the circle. So here you see again that forward differences do the mistake which is here, except that it's flipped here, but because in fact we flip the image. And Conda again, it's perfectly sharp. And again, the figures, we can compute the exact value which we would expect, and the figures are a bit less good, but not very far with Conda's approximation. And this is very mysterious. This is some example where here, for instance, we get a quite sharp example. This is an example computed by my student Corentin, and now let me explain maybe 5 minutes what is here on the right and what is Conda, because the error band we computed for Kruse-Ravia was based on the dual field. So we thought in the end that maybe we were doing something too complicated with this Kruse-Ravia, because if you just in imaging usually you have square grids. So if you have just a square grid and you take differences like that, so a dual variable is naturally something living here and weighting this difference if you want. And if you consider this point of view, so you put your dual variables here, then somehow computing u divergence phi is exactly computing u here times this difference plus this difference. And this is exactly the square Raviart-Thomas interpolation in the middle. So Raviart-Thomas in a square, the Raviart-Thomas field in a square is much simpler than in a triangle. You have flux values on 4 edges, and you just interpolate linearly these two values, and linearly these two values, and you get a vector field which has as a piecewise constant divergence, but it's a true divergence, it's not an approximation, and which has the given flux here, and here the value in the middle is simply the average of this and the average of that. So what is Conda is doing something very strange, putting constraints. So you would like essentially this field to have norm less than 1 when you consider the dual formulation for the total variation. So what is Conda doing is a bit strange. He's looking at maybe this difference here and is asking that this difference is norm less than 1, but if you do that you get very bad results for complicated reasons. So he's considering also differences, I think here and here, where he uses for the vertical field, which is discontinuous, the average on both sides. And he's putting these strange differences, and it's very hard to interpret correctly in terms of something. To do numerical, we don't know how to do numerical analysis with that right now. So he's putting this constraint, and with 3 types of constraints like that, he recovers the result I showed. So we thought about something much simpler. Since our discretization error is based on the fact that our total variation is less than the continuous total variation, and the dual field is just a Raviart-Thomas approximation, why not do that here, simply? So it's something very natural, which I had already done before, but I was not very satisfied by the result. You could consider this Raviart-Thomas field and ask that globally it has norm less than 1. And then you would get a dual ball which is inside the continuous dual ball, because you're just looking at Raviart-Thomas field. So you get a total variation which is smaller than the continuous total variation. So on one hand you have a right inequality. And on the other hand, to build a discrete dual field, you just have to do a Raviart-Thomas projection. So if it's slip sheets, for instance, you get bounds and whatever. So what we simply did here is consider a dual field like that and ask that it's less than 1 here, 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 and here in norm. And by convexity, it means it's less than 1 everywhere. So you just put these 4 constraints, that it's less than 1 in these 4 corners. And you use this dual variable to define your total variation on the square grid. And if you do that, then the proof for the error bond I presented are the same. I mean, you can just use the same proof. So you get a very good error bond. It turns out that I had used that, I had tried this for this kind of problem, and it's not so nice. So I had thought it's not interesting. But for denoising problem with u minus g square, it's very nice. I mean, you see the difference here. Here you have a blurry result in these two directions, and here you have a very sharp recovery. Okay. So the perspective here are always the same, but I've been presenting that for 1 year. I mean, similar results, and still we haven't made those many problems. We would like to use similar things to discretize maybe either currents or lines with some curvature information, things like that. But it's still unclear how to do that precisely. Okay, so I think I will stop here. Thank you for your attention.
There are some questions.
If you want to get the jump across the hole, do you need the gap to be narrow enough to get this?
Oh, here no. Here, in that particular case, no, because you're putting really the condition over there. So, I mean, in any domain, if you put on the boundary the condition that you're half plane, then inside you must be a half plane. It's the shortest path.
If the jump are on the too short end of a long thin hole.
No, but you're talking about a condition which would be different, I think. Of course, if your condition is something like that, it starts to be a bit more complicated. If your condition is not a half plane, but for instance something like this, then of course if the domain is narrow enough, then the solution is here, but if the domain is large, you better cut here.
So you need this to be...
In that case, yes, but for half space, it's always, I mean, the minimum is always a plane or a line or whatever.
On this problem, what is the non-unique solution? What is the other solution?
Yeah, that's something
There are minima too?
I should have talked about. I thought I would not have time, but I have. Yes, exactly. So it's easy. You consider a square, and you consider two different problems. So you consider, okay, a square, and you divide it into triangles, okay? And you arbitrarily select the direction. And you consider a boundary condition 1, 1, 0, 0, for instance, and then a boundary condition, a flipped boundary condition, or flipped triangles, as you prefer. So for instance, 1, 0, 1, 0. Okay. So if you have 1, 1, 0, 0, in both cases, for 1, 1, 0, 0, for instance, it's easy to show that the optimal solution must have gradients in this direction. So the gradient must be all in this direction. And then since you have continuity at the middle point of the edges, it means that here you have the same value because the gradients are like that. So in that case, you will have 1 all here, 0 all here, and only these values are non-unique and can be anything between 0 and 1 essentially, but they must be the same. So you have essentially not one solution but almost, and it's a sharp transition. Okay. If you consider the flipped conditions, then you can show again that the gradient must be in this direction. But this doesn't tell you much. And you can actually build, so doesn't tell you much because it tells you what? It tells you, so yeah, no, it's here, that I should, so the transition should be here, but it's the triangle like that. So even if you put 1/2 here, maybe it tells you what? It tells you that the value here and here should be linked. So this should be 1/2 minus a. This should be, so it tells you there is some symmetry, but you can build up. So I had the slide. I'm sorry, I should have put it. You can build up really solution which has infinite support. Of course, they are very small here. They will decay exponentially, but you can by hand here build values which have gradients like that and which are never 0 here and never 1 here. They just do something like this. So I should have shown an experiment, I think. And what we called adaptive Kreuzer-Raviart, it's really a 2D trick. It's simply saying that if you fix these values, then you can decide that they correspond to a discretization like that or like this. So what you do is select essentially the maximal between the two energies. And you minimize these maximal energies, and it flips automatically if you want the triangles in order to get the right thing. Because if you consider the solution we build here, the smooth solution we build here, which has an energy which is exactly the minimal energy, square root of 2. If we flip the triangle and view it as a discretization on the flipped triangle, it has an energy which is 2. So it's a very bad transition. So if you minimize the max, you get something quite good. But it's only a trick. We can do it 2D. And,
so in this error analysis, when you were postulating the Lipschitz continuity of the dual problem, you have this subproblem where you minimize a very simple functional over all divergences which come from vector fields which have norm less or equal to 1. Does one understand the regularity of the divergence? Because that's the unique part.
the divergence is essentially U.
Yeah.
So one understands a bit the regularity of the divergence, but it's not very regular. I mean, the divergence is simply, you have this divergence Z equals U minus G, I think. So, and essentially you have results saying, for instance, that if G, so depending maybe on convex domain, if G is continuous, then U is continuous. So the divergence is continuous. You have results of that kind. But otherwise,
let's say G is smooth.
if G is smooth, then U can be up to Lipschitz. And if G is BV, then U is BV, and the divergence is BV because U is different from G, and they can jump have different jumps. So divergence can be just BV if G is BV. And if G, of course, if G is L infinity, the divergence. The divergence itself can be bad because if G is just very oscillatory L infinity function, then U will be BV, and this is
Thinking of
yeah. Now, if G is smooth, locally, for instance, you can show that U is up to Lipschitz.
Any other questions? I was wondering, most of your examples are in 2 dimensions. Are there any special difficulties in going to 3 dimensions?
Except for this example, which we have no idea how to transfer in higher dimension. No, most of what I said is the same in 2 or 3 or more. I mean, you could do computation in 3. I think we did not do computation in 3 dimensions.
So I mean, you had this, in a certain sense, quite careful asymptotic error analysis of this boundary. I mean, provided you would understand that really, on the right scale, could you modify this functional, in a way that vanishes in the limit to compensate for these things?
Maybe I don't. We haven't thought of this because we have. Yes, but when you say we have this precise analysis, it's not so precise. We can show that we have some constant which is not 0, and we have some information on the function. But no, you're right. We could improve this information and try to plug it somewhere. I don't know how easy this would be. Yeah, because we can maybe estimate the transition.
it looked to me like you were on the way to develop
Yeah,
an
that's
effective
true.
theory for
Yes.
straight interface, depending.
Yeah, maybe we can find what the transition is. I don't know how I would use it, but no, maybe it's a direction which is interesting.
Last question. Yeah.
Yeah. So you have an error symmetry, the exact discrete solution, right?
Yeah.
In practice, you need to do an optimization problem to find it. How much
Yes.
hard is it to find? I mean,
And that's a good point. That's something I should have mentioned, and actually it's part of the problem here. Of course, if you use this, for instance, finite differences approach, it's quite simple because you have really a dual field which has some point-wise constraints. So there are many algorithms which will give you a reasonable solution in small time, which is not the case, for instance, here. If you consider this kind of dual discretization with this kind of constraint, because what is this constraint? This constraint is a constraint involving this and that. This constraint is involving this and that. This constraint is involving this and so if you write the whole matrix of constraint, you get something which links all the data. So the constraint in one point depends in fact of the constraint in some, of course, not much, but it's a global matrix of constraint which is not pointwise. I mean, it's not a constraint independent in each point. All the constraints are dependent. And numerically, it's much harder so it's much slower to solve this kind of problem. Also, Conda's problem is hard to solve because it also links a lot the constraints.
when you do numerical experiment, maybe use what you call blur or not, maybe the error of the optimization algorithm, right? Because you have not converged enough.
No, I know it's not the case. No, because you can still get, if you have time, you can still get quite precise. You can. These problems are easy. I mean, the one with the quadratic term, because you have a primal and a dual, so you can really estimate a gap. So you know when you have converged on the discrete level. And actually, the analysis we did here is precisely showing that the blur is not something, is not numeric. I mean, the blur is really. That's why we did that sometimes.
So we have